All right, today we want to explore projectiles that are launched at an angle. So we want to be able to identify the types of motion in a projectile launched at an angle. So here is what we've been working with. It's a typical horizontally launched projectile. It has a time of flight of 2.33 seconds and a vertical fall of 26.6 meters, and it will travel 76.2 meters in the horizontal direction. So what happens if it's at a projectile launched at an angle? The trip up is the same as the trip down. We've seen this in something that's thrown up, but this time we've added a horizontal component, and it's the mirror image. And note, the shape of the path is not actually a semicircle, it'll be a parabola. This is important for the regents to know, but PowerPoint only has so many shapes we can choose from. So the whole flight looks something like that. And it'll have a time of flight of 4.66 seconds, which is just the time up plus the time down. And the total distance traveled in the x direction, in the horizontal direction, is 152.4 meters. So to find the velocity in the x direction, we're going to take this total distance and divide it by this total time. And we will get 152.4 meters divided by 4.66 seconds, which is 32.7 meters per second. And we're using our friend v equals d over t because there isn't any kind of acceleration in the x direction. There isn't a force to create an acceleration. So it's the v equals d over t, same as we did for horizontally launched projectiles. Then we need to figure out the angle of launch. Now, on this diagram, we have 22.9 meters per second in the vertical. To get that vertical, we are going to say it is the initial plus AT. We get that just like we do when we throw something up and we throw it and it comes back down. At the top, this right here is going to be 0, and we can call that our initial velocity if we take it as it falls back down to the ground. So the final is going to, this total velocity right here, up here at the top, is going to be the Vy. And we just want it to be the total velocity because we want it to be the one that it would be right here at the top, because that's the vertical component. So this is going to be Vy. And if we plug this in, this is 0. Like I said, it's 9.81 meters per second squared times 2.33, which was given to us. And that's 22.9 meters per second. So to get the angle of launch, it's going to be opposite over adjacent, so it's going to be tangent of 22.9 divided by 32.7. And when we plug it into our calculator, we have to use the inverse of tangent times 22.9 divided by 32.7, and we get 35 degrees. So then what is the velocity of launch? To do this, we look and we see a triangle. This is a resultant, the x and then the y, and it goes from start to finish. And we want this right here. So we do the same procedure we've been doing, and it's going to be Pythagorean's theorem. So we get 39.9 meters per second. So that's what the velocity is right here. It's the actual velocity. So now we have an example problem. It says a football player kicks the ball at 25 meters per second at an angle of 53 degrees above the horizontal. We're going to use 10 meters per second squared for g just to make life easy for right now. What is the vertical speed, the horizontal speed, the time to reach the peak, the max height of the ball, the time to peak and land, so what's the time of flight, and the total distance traveled in the horizontal direction. So to get the vertical speed, it gave us the total initial speed, and it's going to be 25 meters per second. And it told us that that angle was 53 degrees. So then we want to separate it into x and y. So right now it's just asking for Vy, but this would be Vx. So then this is opposite over hypotenuse. So it's sine of 53 is equal to Vy divided by 25. And when we solve, it's 25 meters per second times sine of 53, and we get 20 meters per second for the velocity in the y direction. It would be the initial velocity in the y direction at the top. So then the horizontal speed is found in a similar manner, 25 meters per second, 53 degrees. These are obviously not drawn to scale. This is Vx. And then we're going to say it's cosine 53 degrees because it's adjacent over hypotenuse is equal to Vx over 25. So then it's 25 times cosine of 53. That's what we get. It's 15 meters per second in the horizontal direction. And now we need to save these. We're going to use them later, the Vx and the Vy. So then the time to the peak is, again, that Vy equals At. So the time is equal to the velocity in the y. I'm going to make this clearer. So it's the velocity in the y is equal to A. Remember, anytime there's A, it is in the vertical direction. Just because there isn't any acceleration in the x direction, so you don't have to worry about it there. So that means that we just take that 20 meters per second we found before, divide it by 10 meters per second squared, which is gravity, and it's going to be 2 seconds. The maximum height is going to be d equals 1/2 at squared. This comes from our d equals vit plus 1/2 at squared. And we're saying that this is free fall because we're just dealing with the y direction, and that's the only thing that has acceleration. So the initial velocity is equal to 0. And then we're looking for this distance. A equals g, the time we had from before. It was given to us. And we want the time just for it to fall to the ground. We don't want the total time. So it's going to be 0.5 times 10 meters per second squared times 2 times 2. I messed up. This right here was given to us as 2 seconds. So then the distance is equal to 20 meters when we plug that in. The time to peak and land is the time up plus the time down is equal to the time up and down. So it's 4 seconds because it's just 2 seconds plus 2 seconds equals 4 seconds. And the total distance traveled is v equals d over t. We used that 15 meters per second, which is Vx, and that's distance divided by the total time. And we get 60 meters in the horizontal direction. Okay, so then you can also just think of it as a horizontally launched projectile, but you double whatever needs to get doubled. So you would double the time of flight and the distance of flight. So then what if you're given a velocity, an initial velocity that it starts at? This would be the velocity given. Then this would be the velocity in the x direction, and then the velocity in the y direction. And you would just use SOHCAHTOA. You're given this in the reference table, but you can also use SOHCAHTOA. This is your angle. So it's opposite over hypotenuse, and that's a sine theta, and then a cosine theta in order to find these parts. All right, thank you.